All right, still talking about electrophilic aromatic substitution on a monosubstituted benzene. So here we have anisole. Yeah, I don't think I asked you to learn that name. A methoxy group bonded to a benzene, and we're going to iodinate it. So I2 and iron iodide. Okay, and again, with one substituent on that benzene ring, you've got two ortho positions that are identical, two meta positions that are identical, and a para position. Okay, so we could get ortho-iodoanisole, meta-iodoanisole, or para-iodoanisole. And the way to think about this, there are two ways to think about it. On the last video that I did of nitration of toluene, I looked at the resonance structures of the carbocation intermediate. Here, I'm going to look at the resonance structures of anisole itself. So remember, this is the nucleophile. Anisole is the nucleophile, and I plus, not a star, I plus is the electrophile. So the more electron-rich a position, the faster it's going to react. So got lone pairs on the oxygen. So there's a lone pair on the atom directly bonded to the benzene. This is going to be an electron donor. Right? So it's pushing electrons in. So we get this resonance structure. We can push these around to there. And then we can push these around to there. And the result is, remember, this is the nucleophile. So we're looking for electron density. You've got a negative charge in this resonance structure on the ortho position. The other ortho position has a negative charge in this resonance structure. And then you've got a resonance structure with negative on the para. All right, so an electron donating group is going to put the electrophile, right? If we have an I plus here, we're going to put that I plus on either the ortho position or the para position. We're never going to put it on the meta position with an electron donating group. Okay, so again, ortho and para. And you might be thinking at this point, you've watched two videos and you're like, oh, it always goes ortho or para. It does not. Let's see how much time I have on this one. I'm going to go ahead and do another one. Let's do this reaction not with. Right, I did this example in the electron donating group, electron withdrawing group, right? If we draw these resonance structures, we wind up with carbocations. Sorry. So if we start with a carbonyl bonded to the benzene, right? That's our one substituent, is a ketone. We end up with a positive charge at the ortho position, and these charges then, just like up here, the negative goes ortho, it skips, right? Here, skip one, there, skip one, there. Positive charge is going to do the same thing. So with that electron withdrawing group on there, now the ortho and para positions are electron poor. They have a carbocation there. So with a donor, partial minus ortho and para. With an electron withdrawing group, partial plus ortho and para. Right, so electron withdrawing group here. Donating, ortho and para, electron rich. Withdrawing, ortho and para, electron poor. And so down here, the product we're eventually going to get with nitration puts that substituent, do an iodide, puts that substituent meta. All right, so that's the take home. take home is, if you have one substituent that's an electron donating group, that's going to direct the incoming electrophile to either the ortho or para position. Sterics play a role. If there's other substituents, that plays a role. If you have an electron withdrawing group, it's going to direct the incoming electrophile to the meta position. There's only going to, if it's a mono-substituted benzene, there's only one meta position, right? The two meta positions are identical. If I put I here, I get the same molecules if I put the I here. All right? Again, one last time. Electron donating groups will direct incoming electrophiles ortho and para. An electron withdrawing substituent on the benzene will direct the electrophile